Hello, everyone. Welcome back to another Keep Looking Up with the Ward Beecher Planetarium. My name is Tiffany Woolbrick. I'm our planetarium lecturer, and we have a whole crew out tonight as we talk about the big picture, like the universe big. We'll talk about the structure of the universe and what that looks like and how we know what we know. It's really exciting. I'm so excited for the show, and I hope that you are too. But first things first, let me introduce everyone. First on my screen is Kurt.
Hey, everybody.
That's our planetarium engineer, Kurt Spivey. And joining us again from last week is Dr. John Feldmeyer.
Hey, everybody.
Astronomy professor at YSU. And then we have just kind of in order from what I'm looking at. We have our three students, our three student workers at the planetarium. Jenny.
Hi, everybody.
Eleni.
Hello.
And Nishan.
Hello, everyone.
And then last but definitely not least, we have a guest speaker tonight, Ashley Lemasters.
Everybody.
She is a YSU alum and a former planetarium employee, and we're so happy to have her back to speak a little tonight on her research that relates to the topic tonight. So we're excited to have you guys. A couple of housekeeping notes. This is our last show before we take a break for the summer. We do plan to bring these back. We love doing these shows with you. We love answering your questions and having discussions with you in the comments. If at any point in time you have any questions during our show, please send them in our comments on Facebook. And our students will be moderating that, and they'll either answer you in the chat or they'll mention it to us, and we'll have some discussion live in our video. So we won't be coming back next week again for Keep Looking Up, but we do intend to bring these back probably sometime in August. So look for us there. If you follow our Facebook, we'll make sure to keep you in the loop with all of that information. One other thing I would want to mention, one of the nice things about these shows is that we can talk a little bit about the news and what's happening in astronomy. And today was a very exciting day in space in astronomy. And that was the historic launch of the first launch of astronauts off the US soil in about 9 or 10 years. And also the first launch of astronauts into space with a commercial rocket. So I want to, if you guys saw the launch live earlier this afternoon, we watched it. It was wonderful. It was so exciting. It was really intense because the weather in Florida is not good this time of year, and they didn't know if they were going to be able to go, and they were, and everything was perfect. And astronauts Bob and Doug are currently not on Earth anymore and headed to the International Space Station. Let me just share my screen very briefly. I want to show you just the launch, just a couple of seconds. This is right before the launch earlier today. And what you're seeing here is SpaceX Falcon rocket, which, by the way, this first stage here comes back to Earth, so it can be both reused and studied to make sure it's a really, really good, solid design. And there we have a historic launch today on US soil, and this was the launch pad that Apollo 11 launched, so it's along with many other historic missions. It was really, really exciting, and everything seemed to go perfect. So this is, again, the first time that a commercial company has ever launched astronauts into space, or any humans into space. And so this is the Falcon rocket. On the top there is the Dragon, so the Crew Dragon spacecraft, which will actually physically dock with the International Space Station at some point tomorrow morning, I think roughly 10 a.m. So the live stream for NASA is continuing for the entire 19 hours it takes them to reach the International Space Station. We have the link in our chat if you want to watch that early in the morning. Well, that's early in the morning for some people, but in the morning, and actually see them dock safely on the International Space Station. That'll be really exciting. So it's kind of a new era for space travel for the U.S. right now. It's really exciting. So that was what's happening today, and that's probably why we're all wearing our NASA gear, because we're just like super excited about this. This is really, really neat. But I'm going to hand it over at this point to Eleni. She's going to lead our Star Talk, and after Eleni, we'll have Dr. Feldmeyer, and then we'll end our show this evening with Ashley. Eleni, you ready?
Yep, thank you, Tiffany. So, as always, for our Star Talk, I am using a virtual planetarium program called Stellarium, which is linked down in the comments. It's free. You can download it on your phone or computer. So here I have the date set to tonight, pretty late tonight, about midnight, because there are a lot of things that I want to show you in the sky tonight, and in order to see all of them, this is the best time for viewing. So this is what the sky will look like over Youngstown at about midnight tonight. And this isn't exactly as you would see it, especially over Youngstown, because we do have this problem called light pollution, and that's just where city lights, like headlights from cars, street lights, billboards, shine up and wash out the stars in the nighttime sky. So if you are near a city, you won't see quite this many stars, but most of the things that I am going to show you today are pretty bright, so you should be able to find them. So as you can see, we are facing north tonight, but if we don't have these big red letters here to help us, how do we figure out which direction we're facing? Well, we can use a pattern in the sky that consists of 7 bright stars, and it makes the shape of a big spoon in the sky. You might know what I'm talking about. I am talking about the Big Dipper, which is right over here. So we have these 4 bright stars here that make the cup of the Big Dipper, and these 3 bright stars here make the handle. How does that help us figure out which direction we're facing? Well, the Big Dipper is up all year round over Youngstown, so you can always find it as long as it's not cloudy, and once you found it, you can use these 2 bright stars here on the front edge of the cup. We call these the pointer stars, and trace from the bottom through the top. You'll come to this bright star here, and you may guess that this is the North Star, and you would be correct because it will always point you directly north. So using the Big Dipper, we can find the North Star. And now we can orient ourselves. So now that we know we're facing north, we know that east is over to our right, west is over to our left, and south is behind us. So the first things that I want to focus on tonight are in our western sky. Zoom out a little bit here. So using the Big Dipper, not only can we use the Big Dipper to find the North Star, but we can also use it to find some other things in the sky. You might notice that the handle kind of makes an arc shape, and if you watched our show last week or in the past couple weeks, you've heard this already, but we can use the arc shape of the handle and extend it to arc to this bright star here called Arcturus. And Arcturus is in the brightest star in the constellation called Boötes, the herdsman. So here's the outline for that constellation. I don't know how to draw a herdsman, but there are lots of different ways you can draw this constellation. And the cool thing about constellations is that you can draw them however you see them. I see Boötes as an ice cream cone. So Arcturus is the brightest star. This bright star here is the tip of the cone. So you can trace out the cone like that. And here's their scoop of ice cream on top. Some people also see this as a kite with 2 little tails, but I like to see it as an ice cream cone, especially because we have this constellation right here that looks like a second scoop of ice cream that fell off. This is Corona Borealis, which means the northern crown. because it is shaped like a crown. But we're not done. Once we've arced to Arcturus, we can also spike down to this bright star here called Spica. So we've arced to Arcturus, and now we've spiked down to Spica. Spica is the brightest star in the constellation Virgo. So here's Virgo. A lot of the stars in Virgo are faint, but so it's hard to draw out Virgo's entire body, but sometimes you can see Virgo as a cursive V shape, kind of like this, using these stars here. So that's how I see Virgo. And the reason why I wanted to show you Virgo tonight is because I wanted to show you I wanted to highlight some objects that you can, that you can't see, but some objects in the nighttime sky that you could perhaps see with a telescope. These are called the Messier objects from the Messier catalog. An amateur astronomer was looking for comets and saw these things, and they weren't comets, but he cataloged them anyway, just so he could note that they're not comets. So here are all of the Messier objects, and usually they're just labeled as M followed by a number. So you may have heard of the Andromeda Galaxy referred to as M31. So that's how we talk about these things. And these little red ovals here are all galaxies, and these yellow things here are globular clusters, which if you've been watching all of our episodes of this, you've heard Dr. Durrell talk to you about globular clusters. But I wanted to show you these because you might notice there are a lot of these things in Virgo. This is the Virgo cluster. It's a cluster of galaxies. And it's not a coincidence that they're all together here. And I wanted to show you this because Dr. Feldmeyer in a few minutes is going to tell you more about figuring out why all of these galaxies tend to bunch together like this. So these constellations here, Virgo, Boötes, and Corona Borealis, are all springtime constellations. But you may have noticed it's getting warm outside, the days are getting longer. It is almost summertime. So let's look at some summertime constellations. So tonight, again, the springtime constellations are over in your west. And if we turn around and look east, we will be able to see some of our summertime constellations. So throughout the summer, these constellations are going to be higher and higher in the sky. But right now we're looking over to the east, and the first thing you might notice is this bright pattern here, these three bright stars in the shape of a triangle. We call this the summer triangle. And each of the three stars in the summer triangle are the brightest stars in their respective constellations. These stars are super easy to see. So once you've found the summer triangle, it makes it a lot easier to find three more constellations. The first constellation I want to mention is up here. So this bright star is called Vega, and Vega is the brightest star in the constellation Lyra the Harp. So one way to draw Lyra is, this is the frame of the harp, and you can imagine strings going across it like that. Next, this bright star here. This is Altair, which is the brightest star in Aquila the Eagle. I'm going to get rid of these labels for a second so we can see. So Aquila the Eagle can be drawn like this. This is the head of the eagle. The body comes down like this. One wing here and one wing here. And finally, this star here is Deneb, the brightest star in Cygnus the Swan. So the swan's body comes out like this, and it's got big, beautiful wings. And one really cool thing about Deneb is that Deneb appears to be gliding along the Milky Way. So this cloud of light here is our Milky Way galaxy. If you are in a dark enough area, you may see a faint cloud of light that passes right through the summer triangle. That is the Milky Way galaxy. The Milky Way is actually a disc shape, kind of like a pancake. It's a big, round, flat disc, but in our sky it appears flat because if you imagine looking at a pancake from the side, it looks flat. So that's what we're seeing here. And the summer triangle is really helpful in finding that because it goes right through it. And the last summertime constellation that I want to show you is my favorite one. If you look into the south, the easiest way to find it is by finding this bright reddish star here. This star is called Antares. Antares means anti-Mars, so it kind of looks like Mars, but it's not Mars. If you've seen Mars in the sky, you would notice it's reddish colored too. But this is not Mars, this is a star, this is Antares, and it's the brightest star in the constellation Scorpius, the Scorpion. So Antares makes the heart of the scorpion. Its body is here, its face is here, its tail curls around a little bit below the horizon like that. And this is really easy to remember because it's a summertime constellation in the south, and it's called Scorpius. So all those things start with S. Summertime, south, Scorpius, the scorpion. So again, we looked at our summertime constellations. Over here, we use the Big Dipper. Of course, I have to do this again. We use the Big Dipper to Arcturus in Boötes the herdsman, and to Spike down to Spica in Virgo. But that is all I have, so I'm going to stop sharing my screen now. Actually, before I stop, do you guys have any questions? Are there any questions for me before we move on? All right, it doesn't sound like there are any questions. So I'm going to stop sharing my screen now. Thank you guys, and we can transition over to our next speaker.
Okay, everybody. Tiffany, did you want to talk, or did you want
I just wanted to thank Eleni, and you can take it over from here.
Okay, sorry about that, Eleni. So I get to talk about galaxies, which is one of my favorite things. I'm actually a galaxy person at heart, so I could talk about a lot of things, but what Tiffany asked me to talk about is actually the cosmic web. And that sounds very mysterious, but it's a great excuse to show lots of pretty pictures. So what I'm going to talk about very briefly is what is the cosmic web. And you can actually just see it just from this picture itself. Let me just move this silly thing down. Because what this is a box of universe. Now, it's not the whole universe. It's a very large piece of the universe, and I'm going to explain how you can even get a picture like this. But what we're actually really interested in is not just, oh yes, this is a picture of the universe. We want to talk about how does it change with time. So the reason why there are 3 boxes here is that we are looking at the same piece of the universe at 3 different times. One very early back in the history of the universe, which is close to the Big Bang, so after the Big Bang, and the last box is in the present. And what we're really interested in is how to go from the first box to the third box. And our third speaker is going to talk about, the complications in that. But first, I'm just going to explain what actually is this cosmic web thing. So this is a very, very big picture. So let's go back to a slightly not as big picture. Let's go to the Milky Way. And just to be clear, of course, this is not the Milky Way itself, right? This is an artist's picture of the Milky Way. Astronomers would love to have a spaceship that could fly outside the Milky Way and take a real picture like this, but that's not what we have. So just to be clear, and to quote an old nerd t-shirt, you are here. In other words, you are in that location. This is about the location of the sun around the Milky Way. It's about 25,000 light years out from the center, and the Earth and the solar system are all orbiting around the Milky Way. So this is the area that we live in, and this is the Milky Way galaxy, which is about 100,000 light years across. But the next thing that we want to ask is, okay, so this is the Milky Way. Are there other galaxies? And yes, there are. And what are the closest galaxies to the Milky Way? And can we even see any of them? So it's important to say that all the things that Eleni just mentioned in the talk, you are all inside the Milky Way. Like Arcturus is inside the Milky Way, and Spica is inside the Milky Way. The only things that were outside the Milky Way were those Messier objects, those little red circles that we'll see a little bit later on in this talk. But one kind of fun thing is, what are the closest other galaxies to the Milky Way besides the Milky Way? Okay, so of course, here's a picture of the Milky Way again. This is sort of an old-fashioned picture that I like to show. And the two closest galaxies to the Milky Way are called the Large and Small Magellanic Clouds. Now, they're called that because the explorer Magellan was the first European to, quote, discover them. And I say quote because, of course, people who lived in the Southern Hemisphere known about these a long time. And you can see these with your eyes. They look like little fuzzy clouds. They're not as pretty as these pictures, but I've seen them myself, and they're just little fuzzy little clouds that don't move, and all the other clouds at night do move. So these are two satellite galaxies to the Milky Way, and they're both kind of irregular in shape. We actually think that our Milky Way is slowly tearing these two little galaxies apart. So you can see these with your eye, but you have to be south of the equator to see them. So somewhere in South America or Australia, New Zealand, Africa, someplace like that to see it. Now in the Northern Hemisphere, you can see one galaxy, and that is Andromeda. And it's also known as M31 because of that Messier guy again. And this is a very famous galaxy. It's a big, bright spiral galaxy. It's about the same size as the Milky Way, or maybe a little bit larger. Right below it, it has a little brother galaxy, M32, that you can see right below it. And this galaxy is very famous. It's very pretty. For a while, it was the Apple screensaver. Don't ask me why Apple picked this one, but it is a very pretty galaxy. Now, another nearby galaxy is called M33. And so you see, we already have M31 and M32 and M33. So M33 is another spiral galaxy nearby, but it's not as big or bright and somehow doesn't get the same sort of attention as the Milky Way and Andromeda. But it's an interesting galaxy, and astronomers spend a lot of time looking at it too. And then besides that, there are many little galaxies nearby that look like the picture on the bottom. Let me move my little things over. Hopefully this will make it easier for you to see it. These are dwarf galaxies. And I mention them for a couple of reasons. Is these are actually the most common galaxies in the universe. But they never get the respect they're due because they're tiny and they're not very photogenic, right? They're just little balls of stars. But they actually are the most common galaxy in the universe. So you rarely see them in talks like this. But I wanted to mention, like, this is actually the most common thing. It's like M31 is the big showy diva, and the little dwarf galaxy is like the hardworking person. And so these are the closest galaxies to us, and astronomers came up with an incredibly creative name for this group of galaxies. We call it the local group. Okay, that's really, we really kind of missed out there. We really had a chance to name it something cool. Instead, we called it the local group. So these are the galaxies nearest to us. And this next slide shows you kind of how they're distributed in space. And what you can see is the Milky Way galaxy, and us is at the center of this. And here's the Large and Small Magellanic Clouds. Over here is Andromeda, or M31 and M33. And the main reason I'm showing you this is, one, you can already see the distances between galaxies are huge. We're talking about 1 million and 2 million and 3 million light years. So our local group is 3 million light years across. But the other thing is, if you just look at the distribution of points, you notice galaxies are kind of like people. They like to clump up, right? They notice that most of the other blue dots are these little dwarf galaxies, sort of surround the larger galaxies. So it's like you have little families of galaxies moving around. And you say, why is that? And the short answer, of course, is gravity. Gravity is pulling the galaxies towards each other. But let's sort of keep looking at this idea of how galaxies clump up. Because what I'm going to do now is I'm going to start taking steps away from the Milky Way galaxy, and I'm going to show you different maps of how galaxies are spread out through space. And we're going to get further and further away because the map is going to get bigger each time. And I want you to sort of notice this idea of like, how do the dots that represent the galaxies, are they evenly spread out or are they clumpy? All right, so if we go out a little bit further, right, the local group is still here in the center, and you can see Milky Way and Andromeda, and you can see that most galaxies around us are also in little groups of their own. And in fact, that's true for most galaxies. Most galaxies are in kind of a group environment. So you can think of the groups as like the particular street you live on, or the apartment complex you're in, or a little suburb. So kind of the next one over from the Milky Way is the M81 group. Oh, look, there's another M. This is over here on the right in the center of this image is M81. It's kind of a big, bright galaxy like the Milky Way. Above it is M82, which is sometimes called the cigar galaxy because it looks like a cigar. This is a weird starbursting galaxy, but in all other ways, this little group is very similar to the local group, right? It has a few galaxies of different kinds. There's a lot of little dwarf galaxies. So you can see that, though, that it too is all clumped up. And you can see that most of the nearby galaxies are in little clumps, and then there are big empty spaces where there doesn't seem to be that many galaxies. And we do look for things there, and as far as we can tell, there aren't things in those spaces. Okay, but now let's zoom even further out. And now we're at a much larger scale, right? Again, the Milky Way here is still at 0, 0, and M81 is here. And now you see off to the corner is a huge collection of galaxies. And this is called the Virgo cluster, because this is when you look through the constellation of Virgo and go past the stars of Virgo, and you keep going, you eventually run into these galaxies. And so this is the first galaxy cluster. It's the closest galaxy cluster to the Milky Way. And there's about 10,000 bright galaxies in the Virgo cluster. And over here on the right is a picture of a lot of these. And by now, I think you've gotten the joke, but right here is M87 in the center of the image. Over down and to the right is M86 and M84. Now, not all the galaxies you see in this picture have M numbers, but a lot of them do, because they're very big and very bright. So this is our first galaxy cluster, and the way to think about it is it's like a city. If the local group is like the street that you live on, the Virgo cluster is a large city with a lot of action and a lot of drama. About 10% of all galaxies are inside of galaxy clusters. Most are in these groups. But you get the idea that now things are even clumpier. And again, you can see this pattern where some stuff is in little clumps, and then there kind of are big empty spaces where there doesn't seem to be a lot of galaxies. And I forgot to mention, these pictures, these really nice maps of the galaxies are from a project that I didn't do, but another group of astronomers did. It's called Cosmography of the Local Universe. And I mention that because they've made some very nice movies of like zooming out of this quickly. And I would show them to you, except they're a little long, and frankly, you can see them for yourself. And we have the links in the description. And so I really encourage you, if like this really interests you, is watch those movies because they're pretty amazing. Okay, so this is the last picture from the Cosmography of the Local Universe. And now we've expanded out even more. And again, notice like here, I was just bragging about this like Virgo supercluster. That's that little blob there. And now you can see there are even bigger galaxy clusters right? There's a very famous one sort of at the top. It's called the Coma cluster of galaxies. This is one of the densest and most rich galaxy clusters in the entire universe that we found. You can see there's this structure that's been discovered, which is called the Great Wall. All right, and you can see that there are huge empty spaces where there are relatively few galaxies. Now remember, what you're seeing here is kind of a three-dimensional picture, and what these red spots are where there's a huge number of galaxies, the blue and green are where there's a moderate amount, and the light blue is the small ones. And our local group now is this tiny little dot in the center, this little green kind of teal spot. So the universe, the first thing to take away from this is the universe is very clumpy at large scales. Galaxies like to clump up, and then there are what are called, those are clusters, and then empty spots astronomers call voids, because there doesn't seem to be a lot of galaxies in those places. So the next question is, well, why does this happen? And so that takes us partially to what our speaker is going to talk about, but to sort of set her up, I'm going to talk about how the Big Bang started. And of course, you could spend a whole 20 minutes talking about just this slide, so we're not going to do that. But over here on the left is the beginning of the universe, the Big Bang, and time goes to the right. Now, the first light we can see from the universe is not the Big Bang. It's this time here at 400,000 years after the Big Bang. So this blue-green stuff is called the cosmic microwave background radiation. And so that's the very first thing we can observe in the universe. And all the stuff that I've been talking about in the previous slides are way over here on the right. These are nearby galaxies, and we're seeing them as they were, 100 million years ago or 200 million years ago. So the basic puzzle is the following. So right here at the early universe, the universe is not very clumpy. In fact, the universe back then is smoother than a piece of paper. Only small changes are even possible, which is the little blue and green things you see, and that's 1 part in 100,000. If you had a piece of paper, a real piece of paper is bumpier than that, like a normal sheet of paper. So that's very strange, right? So the universe is very not clumpy there. But I just showed you lots of pictures that showed the universe is much clumpier today. And so we have to figure out how to go from this very smooth thing to this very clumpy thing. And we know the basic idea, it's gravity, but the details are kind of important here, right? Like the stuff that I'm skipping over in this talk that our speaker will talk a little bit about, things like dark energy and dark matter, they affect what happens between those two spots. So how do we figure out how to go from the thing on the left, which is smooth, to the thing on the right, which is clumpy? And what astronomers have done is there's sort of two ways that we've tried to figure this out. So the first way is we use very big computers. So in that case, you use a supercomputer to actually make a simulation of a piece of the universe. So you take information about what the early universe is like, you take the laws of physics, and then you go forward in time with your simulation, and you see if your simulation matches up with reality, right? This is a lot like sort of weather forecasting, where you know what the conditions are today, and you take the laws of physics and what our atmosphere does, and then you go forward in time and see, well, is it going to rain tomorrow or not? So obviously the details of that are super complicated, and we're not going to go through them right now, but that's one way to approach this. The other way to approach this is to sort of keep doing what I was showing you, which is look at how galaxies are spread out through space and see how the clumpiness changes with time, right? So I sort of showed you what the local universe, the very close to the Milky Way, look like in clumpiness. But you could do this, 1 billion light years away from us, and 2 billion light years away from us, and 3 billion light years away from us, and see how things change with time. And so just to come back to the original picture, what I was showing you was a computer simulation. So in this simulation, which was, done by a supercomputer over months of time, is an immense piece of the universe. Like, in fact, the box is, about 3 billion light years across. And every little dot represents one galaxy like the Milky Way. So over time, you notice in the beginning, things are not very clumpy. There's a few clumps here and there. And gravity starts pulling the galaxies into small groups and galaxy clusters. We also know that galaxies will merge together. Like, we do believe that the Andromeda galaxy will eventually merge with the Milky Way in about 4 billion years. So it's nothing to worry about, but we do think it's going to happen. And so eventually there will be a Milk-Dromeda galaxy. But we think this happens everywhere in the universe. And so the final picture is what we think our universe looks like at the largest scales. And for a lot of people, it looks like a spider web. And so that's why we actually call it the cosmic web. You can see there's this filamentary structure with kind of clumps where there are galaxy clusters. That's what the yellow kind of pieces are. And the sort of ghostly white and purple parts are the filaments of different structures. And so it's understanding this cosmic web by observing it through time that we're going to talk about for the rest of today. Okay, so that is it for me. Are there any questions that people would like to ask?
Ben asks us, why is the Milky Way flat?
So the Milky Way is flat because the original gas that made it is rotating. So this is kind of a fact in astronomy everywhere. And it's the same reason why the solar system planets are kind of in a plane, and why stuff falling into a black hole is often in a plane. So it's basically things that spin want to keep on spinning. And this is, the big words for this is conservation of angular momentum. But I'll show you with my hands, right? So if you have this big blob of gas and it's rotating, what will happen is as it falls in from gravity, it will flatten out and make a sort of disk configuration. And so this happens everywhere. You can also think about, an example I use in my classes is think about hand-tossed pizza, right? One way to sort of there are many ways to make pizza, but a fun one that we've hopefully all seen is where somebody throws up dough, but then also rotates it. And that tends to stretch the dough out into sort of a disk configuration. That's not quite gravity, but it's the same idea, is that things that spin want to keep on spinning.
We had one more question.
Okay.
In the distant future, will the overall structure of the universe resemble a bunch of spherical sections of matter or galaxies, much like solar systems consist of essentially round objects, or will it always have some form of web structure?
So the simulations that I've seen always imply a web structure. It will, one big factor about why it will stay that way is something called dark energy, which our next speaker will talk about, is that the universe is continuing to expand while these galaxies are falling in. So even though some galaxies close to us, like in the local group, will merge and become a larger galaxy, say like the Virgo cluster, M87 will not fall in to the Milky Way, right? It's just simply too far away. And the space between galaxies will continue to get larger over cosmic time. So over time, eventually galaxy merging will slow down or stop.
Wow, well, thank you, Dr. Feldmeyer, again for a wonderful talk. If you guys have more questions for him or for Ashley, please feel free to put those in the comments. We'd love to have some discussion at any time. But I will, at this point, hand it over to Ashley Lemasters.
All right, thank you very much. So I am going to talk to you all today about the unknown universe, dark energy. So, in the beginning, some preliminary knowledge. In the early 1990s, we thought we had a pretty good picture of the universe. We were studying light from distant galaxies, and light was shifted towards the red end of the spectrum as it traveled through space. So, and we discovered something really, really interesting, that nearly everything was moving away from us. This red shifted light meant that the light was taking far longer to reach us than it usually should have. Now, I say nearly everything's moving away from us because there is one thing in our universe that is actually barreling straight towards us. And that is what Dr. Feldmayer talked about. This is the Andromeda Galaxy. It is blue shifted, which means it's headed right towards us at a colossal speed of 110 kilometers a second. But don't worry, if that day comes, when that day comes, and the Andromeda and Milky Way collide, you can just take that day off of work. But so that's the only thing that's coming towards us. Everything else is moving away. So as we're peering into the cosmos, we do know that nearly everything's moving away from us. That meant that the universe itself was expanding. But people figured, well, there is a lot of matter in our universe, so gravity is probably just going to take over, and the expansion would probably slow down. Some people even thought, well, this expansion, it's going to stop. Gravity is probably going to pull everything together, and there was a theory that there was going to be a big crunch where gravity eventually pulled everything together, and, well, the end probably wouldn't be too pretty for us. So that was our idea in the 1990s. Until a new contender entered the field in 1998, we had the Hubble Space Telescope. For a cool $2.5 billion, it can be yours. But Hubble started analyzing the light from supernova remnants farther than we have ever been before. Hubble really did open up brand new discoveries and pathways to things we've never even imagined. And that rang true for what we thought of our universe as well. So it started gathering light from these supernova remnants. The one on top there is the Crab Nebula, and the one on the bottom is Tycho Brahe's supernova remnant. And as it was studying these objects, it realized that the supernovae, those were a bit too dim to really be what they're at now. Those really didn't have enough light coming from them. We realized that the farther back we looked, the faster things were moving away from us, which was startling and led to a really big revelation that the expansion of our universe was accelerating. It wasn't slowing down. Gravity was going to do nothing to it. So this completely turned astronomy on its head. So our current picture, I think Dr. Feldmayer had a better one than me, but our current picture is that we had the Big Bang here, and then, move forward his head, sorry about that. We do have the cosmic microwave background, and then stars developed, galaxies developed, and then roughly about 5 billion years ago, that expansion ramped up by a lot. Every moment that the universe is expanding, it's going faster the next moment. Which, well, why? That is absolutely insane. It turned astronomy completely on its head. No one knew what was causing this expansion, but we definitely knew it was there by studying the cosmos around us. So we have this brand new thing happening to our universe. So what exactly does that mean for our universe? So as we've gained more knowledge, here I have a lovely graph of the energy and mass in our universe. That little blue portion there, that is roughly 4% of all of the energy and matter in our universe. That is something that we call baryonic matter. So baryonic matter is basically atoms, but that's not just atoms. That section of the universe, 4%, that is me, that is you, that is the computer I'm using, the phone you have in your pocket, that is the air we breathe, that is the gas and dust in our galaxy, that is the stars themselves. That is everything we have ever seen. That is only 4% of our universe, which is absolutely crazy. That is awesome. Okay, so 4%, that's what we are. What about this next section? Well, that is about 21% of our universe. That is something we call dark matter, which is a whole talk in and of itself. It's really cool. But that makes up 21% of our universe, which leaves the majority. This is 75%, and this majority is the stuff that's causing the universe's expansion to accelerate. 75% of everything that exists is this mysterious thing that's causing our universe's expansion to accelerate. All right, so we've discovered this thing. We know it's there. It has big impact on our universe. Now, we all know that astronomers are like the absolute best with naming things. So what do we call it? Well, we call it dark energy, which usually, that does sound pretty cool. It sounds mysterious because we don't know much about it. But the only problem is that, well, as much as we don't know about it, we do know two things about dark energy. The first one being is that it's not exactly dark. And, well, the second one being, we actually don't know if it's energy. I know, we are so good with naming things. Now, a cool fact about dark energy is that the US Department of Energy actually funded experiments into dark energy to see if they could perhaps use it to power the United States. Unfortunately, you can't really harness dark energy, but they still do fund some projects to be like, it's like, you do know that you can't really harness it. They're like, it's fine. So that's a cool fact there. So if we know it's not really dark and it may not even be energy, what is it? We have no idea, which is really funny. There are some theories, but this is such a relatively new discovery, and we still need to peer further and farther and do more experiments with this. It literally is one of the biggest mysteries of science, and we don't know what it is. We do have some theories. It could be that it is a property of space. Another theory is that it could be an exotic new particle or field that we just haven't discovered yet. Or it could be, perhaps the most upsetting, that our entire theory of gravity is wrong. It could be that gravity on very large scales acts very differently. But the coolest part about this is that we really don't know. We are genuinely on the forefront of this discovery, just treading out into this exciting new venture. Okay, so how do you study something that doesn't really interact with anything? Well, it's not a fruitless endeavor. There are projects going on that we have good ties to. One experiment searching for dark energy is HETDIX, which I may or may not be a little bit biased with because I worked on it in undergrad. HETDIX stands for the Hubble Telescope Dark Energy Experiment, and a quote from their site is that HETDIX will be the first major experiment to search for dark energy. It will use the giant Hubble telescope at McDonald Observatory and a set of spectrographs to map the three-dimensional positions of 1 million galaxies. So on the bottom left there, we see that that is the McDonald Observatory. And then over here on the right is an example of the spectra that those spectrographs are going to get. And HETDIX is really cool. Not only is HETDIX trying to illuminate the darkness by trying to find dark energy, but we can also get new discoveries and all kinds of awesome, interesting data from these projects that are going on. One such thing is that during my research with HETDIX, we discovered a brand new object. This is an actual ring-like object. It could be a ring galaxy. It's not a scattered light pattern, and it has been verified by Sloan. So even in venturing out into seeing what exactly our cosmos contains, we can find even different interesting things that aren't exactly related, which is pretty cool. Another telescope that was on the Earth, off the Earth, is the Nancy Grace Roman Space Telescope, previously known as WFIRST. This is a space-based telescope that is going up sometime in the 2020s. They don't have like an exact launch date for it just yet, but this telescope is also going to be searching for dark energy. It has a view, so a field of view, 100 times that of Hubble, which is really cool. It has a 2.4 meter mirror. It is 1 million miles away from Earth, so it's going to sit at a stable Lagrangian 2 point out in space. and it's going to look for 1 billion galaxies. On the right there, we have the CGI instrument. It's the coronagraph. That is one of the instruments that is going to be searching for the remnants and the telltale signs of dark energy. So that is all I have for you guys. Dark energy is one of the biggest mysteries we have out there. There's so much to learn, so much to discover. And thank you. Does anybody have any questions?
I wasn't seeing any questions. Did anyone else see any?
I haven't seen any.
Okay, well, we have a couple of minutes, which I'm really excited about because we can, since this is our last show of the summer, you can consider this sort of a question free-for-all. So if you have any questions about space or anything, ask them in the comments and we will just sort of take turns and answer some of those. Does anyone know the launch date for this new telescope that Ashley mentioned? Was it the Nancy? What was it? I know it is W first, but they just named it.
Nancy Grace Roman Space Telescope.
Yeah. Does anyone know the launch date of that? I forgot myself, but I know that it's in the next few years.
The internet says 2025.
Okay, so in a few years, we'll have JWST up there first. I do want to thank you, Ashley, so much, and Dr. Feldmeyer for a wonderful talks. One of the things I appreciate about these virtual programs is being able to sort of deep dive into specific areas of astronomy and giving opportunities to share how we know the things we know. Because usually that story is just as interesting. Looks like Eric is asking, do you think it's possible to utilize dark energy in the future to power Earth? I guess the Department of Energy thinks so.
So currently, they don't think that we're going to be able to, but I think Dr. Feldmeyer has more to say about that.
Yeah, so this is a funny story, but I think what people have to realize is physics in the United States is funded by like two groups of people, well, three, the Department of Defense, obviously, but then the National Science Foundation. But the Department of Energy has been funding particle physics almost for 60 or 70 years. And the funny thing is, until very recently, astronomers sort of couldn't be allowed to touch that money. It was sort of like hands off. And then basically one of the Department of Energy people basically said, well, what you're doing is really interesting, so we're going to call it energy so that you can do research in it. And we're like, thank you. Yeah. And then, like all astronomers everywhere, we started writing grant proposals. I don't think the Department of Energy really thinks they were going to get something practical out of dark energy, but I think understanding dark energy answers a lot of other exciting questions. So they're perfectly fine with that. And it is actually a very small piece of the Department of Energy's total budget. So that's their excuse, basically.
And I think that this is, as Ashley mentioned, we're just at the beginning. And so uncovering these answers in the next few years, in the next few decades, I'm not saying we'll have all of the answers by then, but learning that as we go that's why scientists are scientists. That's what brings us to work every day and gets us really excited. So that's why dark energy is so cool for astronomers and scientists. I think for the general public, it also has just a really cool name, really mysterious. Kurt, Charles is asking about your background. What is it?
Oh, didn't you watch the launch today? Yeah, I'm in Earth orbit.
Oh, were you one of the stowaways?
Yeah.
Okay.
I was that little dragon that was floating around.
Best vacation ever.
All right. Well, hey, this is wonderful. feel free to continue asking questions in the comments, even if you watch this later. We also upload these to YouTube, so to our YouTube channel, at WB Planetarium. So you feel free to find us there at another time, or share it with friends who maybe aren't on Facebook. I hope that you guys all have a wonderful summer, and that you go out at some point and you look up and you see you observe the sky that we all share together. Does anyone have any last minute things they want to say before we head out?
I want to mention that, as Tiffany said at the beginning, we are planning on bringing back these virtual shows in the fall. That does not mean that we aren't planning on being back in the planetarium in the fall. We are actually still trying to work out exactly what that means with the new regulations and the distancing. We're working out all that stuff, what our public schedule in the planetarium will look like as opposed to our public schedule online. So it's one of the things that we're going to be working on while we're not doing these shows.
Absolutely. And you know, safety is our first concern, but we do miss you guys. We miss the dome. We want to see you guys back. And so just stay tuned with us. We will make any announcements on Facebook, on our website, and just keep you up to date as we know, but we really don't know anything yet either. So bear with us. Thank you guys again so much. I think we'll wrap up. Thanks for joining us again. We'll see you in August. And remember,
Happy summer solstice.
Oh, happy summer solstice, June 20th. We won't be around for that one, but it's good times. Kurt will be talking about that on the local news station.
WFMJ on Monday.
Yep, this Monday. So if you're a Youngstown native and want to watch that, you'll learn all about the summer solstice with Kurt. Thank you all again, and keep looking up.